I'm continuing to optimize the software sketch on this LS30 rotary joystick interface for the two joysticks to send keystrokes over USB so that an emulator can monitor the two joysticks for clockwise or counterclockwise movements and send out a keystroke for the emulator to work. And I have two different rotary joysticks. I have the LS30 original and this Happ Controls version of a rotary joystick with 12 switches on it as well. Works the same, has the same sort of cable to plug in as a substitute. But I want to characterize how these two different styles of joystick work. For example, looking at the timing between switch contacts, try to help figure out how this whole thing works so that the software in this board can monitor and send the keystrokes as best as possible to represent the gameplay of the original hardware. But first, what is this all about? What are these joysticks for? There's several games that use this style of joystick where rotating the joystick itself will produce signals for clockwise or counterclockwise movements to the game. And the character on the screen can do things like change the direction the character is facing so they can run one way and be shooting an enemy in the other direction. So we want to be able to interpret those special movements so that the game emulator can also use the original hardware if it's available. Otherwise, you might have to have dedicated separate arcade buttons to press to rotate one way or the other, and it's not as much fun. So to characterize how the signals work so that we can read them in with our project, I made this little test board so I can plug in the joystick, and it has a bunch of pull-up resistors and headers that I can plug test points in and put oscilloscope probes. There's also 5-volt and ground connections here. So it simulates the joystick being plugged into a game system. And I have 4 scope probe channels hooked up consecutively. So when I'm in the right position, I can rotate 4 times or back 4 times. And on the scope, I can see those 4 channels switching between high, the default, when nothing's happening, and low, when the switch is actually being pressed. The joystick is in that position. So I want to try things like turning slowly in both directions, as well as quickly as possible, more than you would realistically ever do, and just see how these signals look so we can learn how to read them. Here, from the top trace downward, represents 4 continuous positions on the joystick. I set the vertical scale bigger on the top trace because it was easier to trigger. I set the scope up so that when the signal goes from high to low, we will start capturing what happens after. And this scope can get a bit quirky when it's trying to trigger within a small vertical scale. So I increased this one, and the rest of them are just compressed down so they can fit and we can still see what's happening. So when the switch is not in a certain position, the pull-up resistor brings it to 5 volts. And when you bring the switch contact into a certain spot, that pin gets connected to ground. So here, the joystick just moved and landed into a certain position. I was going as fast as I could, so then it quickly moved on from there, and the line got pulled high, and then it moved into the next position, so that one went low. Then I kept spinning fast, so the next one went low for a bit, and then I finally stopped here, and you can see it was held in place longer than back here, since I slowed down and it was still in that spot. Then I turned around the direction and quickly started going backwards. So once I had a few movements, it was only held down a small time. Then I got to the original joystick position. So here, looking at the timing, I'm at 20 milliseconds per division. So I can start to analyze how fast is this capable of changing. This here was the quickest one out of this test. So if I change this and line it up, it looks like maybe 16 or 17 milliseconds. This joystick position was held in place while I quickly was spinning through. and the slowest one when I was slowing down to change directions, 20 per division, means we were there for 40 milliseconds versus the 15 or so. So this will help me understand what do I need to do in software when reading in this stuff, and how quickly do I need to respond. Another observation is, even though we need to zoom in to see the switch contact bounce better, these are relatively clean transitions both into and out of a switch contact position. So that makes it a lot easier to debounce and clean it all up. Also, it has a break before make operation, meaning when you're going from one position to the next one directly beside, there's no overlap where this one is still on and then this one is starting to come on, so you're trying to interpret which way am I going. The way this one works, by the time you read that you're in a new spot, you've already released the original spot. So there's this small idle time in between transitions where nothing is pressed. And another thing we might want to know is if we're considering a new joystick position to be occurring as soon as we start seeing that we've gone low because the switch is being made, we don't really care how long it's held low as long as it's a valid debounced low. We don't care when it goes high again, because all we're doing is reacting when we know we are trying to get into this position, and we're sending out a USB keyboard keypress. So then all we care about is the next time a different switch goes low. So in this case, the green trace here goes low about 40 milliseconds after the previous position went low. Then going from the green to the yellow, it's a lot faster. It's maybe within just under 30 milliseconds from one contact being made to the next one. And the same over here when we're really going fast. This yellow trace again shows we get into that position. And then it's about just under 30 milliseconds later, the green trace is showing we rotated to the next position. And I did a different measurement before where I was more zoomed in. Basically, I was seeing 22 milliseconds from one contact starting out until the next one is starting out. So putting all those observations together, from the time we start to see a switch contact going into a new position until, worst case, we are quickly rotating and we get to the next position, we may have around at least 15 milliseconds of time to read a valid switch position. And overall, from that one starting until the next one starting, we might have 22 milliseconds at least to get everything accomplished that we want to do in between picking up one movement to picking up the next movement. So one previous problem I was having, every time we detect a new position, we need to send out a USB keyboard keypress. And currently what I'm doing in the sketch, I'm allowing the keypress to be held down as if you're pushing a key on a keyboard for 100 milliseconds in order for the computer to have time to recognize it, including the emulation software that's running. Because there's all kinds of latencies. You send out the USB keystroke command, the computer has to get around to reading it and then figuring out what to do with it. The software running has to read it in and then figure out what it wants to do with it. So it turned out at least 100 milliseconds of holding a key down and then releasing it on every joystick movement is what was needed. So if this joystick is going from one position to the next, possibly with only 22 milliseconds between, we still need to hold a key press down for the original one for 100 milliseconds and then do a key press for representing that we moved again and again and again and again. So this is one way we might miss keystrokes if we're reading this in real time and just saying, there's a joystick movement, send out a keystroke, and now read again. Well, we've now missed possibly 3 or 4 key presses if we're going really fast. If we're going reasonably slow, there's lots of time. So one of the changes I made now, I'm not trying to process and send keystrokes in real time as blocking code where we can't continue reading. So I've set up a ring buffer or circular buffer where I'm sending out keystrokes, but at the same time in the background, I'm monitoring quickly everything going on And every time there's a new movement on a joystick, I figure out if it goes clockwise or counterclockwise based on the pattern, and I add that information into the buffer for both joystick player 1 and player 2. So if a buffer is empty, it means there's no pending actions to send keystrokes out for. But as we have a new movement, that buffer is going to have one entry for every joystick movement, and that entry is going to say whether we want it to go clockwise or counterclockwise in sequence. So when we make a keystroke, we check the buffer. If the buffer says the next movement you need to do is counterclockwise, we now send out a counterclockwise keyboard keypress, and when that's done, we check the buffer and we see now we got to go another direction or the same one again, or there's no further action. So we can accumulate all these movements and just send them out as slow keystrokes as we get time. So doing this as fast as possible, I think right here, twisting back and forth, I'm able to get maybe 7 or 8 at best. And by then, it's not realistic. You're not playing a game like that anyway. Usually you're running around and then you might be going a couple this way, a couple that way. So in software for now, it's configurable, but I set it to store up to 20 keystrokes for both players each. So theoretically, I can get behind by 20 movements, but in real terms, the key presses are going to empty the buffer and will be nowhere near 20 pending keystrokes. So it should keep up to date. Now, if I try to zoom in and look at more of the switch bouncing, it may pick up bounce on both rising and falling edges because I set the scope to trigger when we go from high to low. But if it's bouncing on both edges, moving in and out of this position, it's going to be doing a bunch of high-low, and then high-low. So we may sometimes trigger both edges. I'm just going to zoom in. So that's 5 milliseconds per division. We have like 60 milliseconds of time showing on the screen after this goes low. If I do the same thing over on the other edge, where we're coming out of that switch press, 60 or so milliseconds before this, it's all relatively clean as well. But I can try to do this until I get a rougher transition. Now we're at 500 microseconds per division, so that's only 500 microseconds of noise. So it's really hard to make this thing have a lot of contact bounce, but there's an example of bounce in general. We're at 200 microseconds per division, so we see that we started to get a little noise here as we started moving. So let's say 700 or 800 microseconds, we stabilized, so we had a bunch of high-low transitions. From looking at this, a couple of milliseconds of debounce should totally become immune to this. So for now, I'm just going to take this Happ Controls joystick out, and I'll put the yellow handle LS30 and compare. So now I have the authentic joystick. So I'll check for the zoomed in contact bounce because I'm already set up on the scope. And that's looking similar. We're at 2 milliseconds per division, and when a transition occurs, there's really nothing noisy going on very much after the transition. So here it is at 500 microseconds per division. It looks similar. Once we get a transition, there's barely any bouncing on the contacts. Although, I believe, because I bought these used on eBay, I don't even know when, between 20 and 25 years ago, they were out of an original arcade. I don't know if the contacts are dirtier in general. We get a little more noise. The other Happ Controls ones I bought brand new, so they were only ever used at times like this. Nothing practical. So aside from that, the behavior for the timing on the switch bounce is similar. Now if I zoom out, I'm at 50 milliseconds per division. So I'm going to try to quickly go forward and back. I wonder, can I zoom this in now? So from a perspective of 20 milliseconds per division, going quickly on the yellow handle joystick, once a switch contact starts being put in position, it looks like it's low for maybe 35 milliseconds. The next one is low for 40 milliseconds. The next one's probably about the same. And then we had this longer one at the end of rotation because I then went the other direction. so I had to slow down and then speed up again going the other way, between 45 and 50 milliseconds on this yellow, maybe 38 milliseconds low on the green, and so on. And also, it's not the same behavior between positions as that other Happ joystick. The other one would break the connection before making the next one, but these are overlapping on this joystick. So this one does operate a little different. Going over to the initial movement, when we were leaving this position and going into the next one, the next contact started going low while the first one was still low, and then it released. So this one is make before break. So really, software should be immune to that because, again, we're only looking at the initial high to low transition to say we want to consider a button press and then another button press. It shouldn't matter historically by the time we're looking at detecting a new one, well, what's the old one currently doing? We already know it's stale information. But at least we know the timing of when we move quickly. These are being held low. On the other joystick, we were seeing 15 milliseconds of minimum low time. This one, it holds it even longer, so we have more time to get to it in software. So as long as the switch bounce is about the same on both joysticks, and we know now what kind of time frame we're looking at to be able to read these in and process them, at least now we can work on the sketch and optimize everything there. For the sketch that seems to currently work the best with both joysticks and their somewhat different behavior with how they make and break contact, I have notes here. For example, I'm using the bounce library for button debouncing, and the most recent addition is this ring buffer to store key presses until I can get around to sending them. So that file is just included in the sketch folder. There's no library to install. And now I have this new enumeration to store whether an upcoming USB output keystroke will indicate clockwise or counterclockwise buffered movements for a given joystick. I set it up so that each joystick can buffer up to 20 keystrokes while waiting for a chance to send those out. So it's joystick 1 and 2 buffer. Here's where we can set which keys on the keyboard will rotate each joystick clockwise or counterclockwise. So the emulator will be set to read those in. And there's some sensitivity settings maybe in the emulator where you can make it respond quicker or slower to key presses. Tweaking those settings may help, along with tweaking the sketch here. When sending a USB keyboard keystroke, I'm controlling the amount of time the key is being pressed. So if I want to hit R to rotate joystick 1 clockwise, I hold down the R key for 110 milliseconds. If I was going any shorter of a duration there, at least on the system I was testing on, every so many rotation attempts, it would not pick it up. So I just kind of kept increasing this key press duration for how long the key is held down. And at 110 milliseconds, it seems like it was finally registering all of my keystrokes. I just chose an arbitrary button input switch debounce of 10 milliseconds, knowing that it's probably very stable after 1 or 2 milliseconds, but also knowing I have over 20 milliseconds until the next switch has to be read if I'm going as fast as I can. So I figure 10 milliseconds is a good trade-off to definitely give enough time to debounce, and there's still lots of time until the next possible keystroke needs to be handled. So then I should be able to just keep collecting joystick movements, throwing them in this buffer, and sending them out at 110 milliseconds per USB key press, and this seems to keep running smoothly. The rest is all general stuff for processing the joysticks that we've looked at in previous videos. So in the main loop, we're running 3 separate functions repeatedly. First, I just read in and debounce all of the joystick buttons. Then I process if there's been a change, and if needed, I can add a pending keystroke to the buffer for whichever player has rotations that need to be sent out. And then processing the keystrokes is where we look at the buffer, see if one of the players has an upcoming keystroke needed, and it will send it out and check the timing, make sure it's held down enough before releasing the button, check the buffer, and then as we keep going through looping, if there's more keys in the buffer, it will send out the next keystroke and just keep reading the joysticks and doing what's needed. So here for processing the joysticks, if it determines there's been a change in position on one of the joysticks, once it figures out if it's clockwise on joystick 1 or counterclockwise or joystick 2 clockwise or counterclockwise, for the ring buffer to buffer keystrokes, we push into the buffer a placeholder for a clockwise motion on joystick 1, or we push a counterclockwise pending keyboard keypress for joystick 1 or joystick 2. So that just starts filling up the 20 element buffer. And down when we are processing keystrokes, we check if there's anything in the buffer, so there's greater than 0 elements in there waiting to be processed. We check if we are currently sending out a USB keystroke for that joystick, because we need to wait and send out the next keystroke after the current one's done. So when we are ready, if we do have to send out another joystick keystroke, we use this pop command to take the next joystick movement out of the buffer. Then we check, is it clockwise or counterclockwise? And then we start another USB keyboard keypress, either for the joystick 1 clockwise or counterclockwise keystroke, and we start a timer. So ultimately it's going to hold down this keystroke until, in this case, 110 milliseconds for the keypress. When it's released and it gets back to this loop, again it'll check, does this joystick have more pending keystrokes in the buffer? And again, are we currently in the middle of sending another one? If so, we just wait. When it is time, if there is something else in the buffer, start pressing the appropriate key, start the timer again, and eventually we have nothing left in the buffer, so there's no more USB keystrokes to send, and we're just back to reading in joysticks, checking if there's any movement, and checking if there's any keystrokes to process. So let's see how this works on the emulator. Now I have the USB joystick interface hooked up to this computer with Windows 10. I'm using a USB keyboard as well, so I'll get the game started. So the character is right here, and just using the keyboard, I want to get a sense for it. Pressing a key, it just actually went twice with one hit. So I'm going to try and do clean single rotate presses. It just did twice actually for one hit. Maybe I held it down too long and I could fix the sensitivity in there. But generally, yeah, it did 2 again. So if I go the other way, it's just a matter of getting used to it as well. So now if I just go back and forth, it just went 2 the other way. So the whole thing is just subjective anyway as to if this character is rotating not as expected, maybe tweaking the settings. But now I'll go get the real joystick. So I'm going to go one position at a time. It's even seeming cleaner than when I was trying to do it on the keyboard, just probably because on the keyboard I'm holding it down sometimes too long. So I'll go the other way now. And I'm probably going to have to start another game. So this time I'm going to try going one position forward and then back. So that seems relatively okay. If I go the other way and back, now if I try to go 2 positions over and back, I should be going sideways and back up. I went too slow there. It's hard to do like this with my arms outstretched as well. But doing it quick like this is where I was having trouble before. Now it seems to be keeping up because it's buffering my joystick movements and just sending out the USB keys whenever it gets a chance, instead of trying to do it in real time. So now if I go 3, if I try to calibrate for 3 rotations, there's 3 and then back. So that seems relatively consistent. I'll wait for this to end. And so if I just try to do this naturally, yeah, I can get like 3. I'm trying to see what's the most realistic. If I try to go quickly, 5. I just counted 5 clicks and I think that is 5. So if I try to go 5 back, maybe it was 6, I don't know. Oh yeah, the joystick was in between. So I'll try 5 again, so it should end up down here. It's hard, I counted 6. It's hard to do that. I'll go back, 5. Okay, and 5 back, sort of. It's hard to do, but really, so I'm just going to do some motions here. So I'm going to think, okay, what do I want to do? I want to start aiming straight up. So what do? Now, if I want to go all the way to the other side, I think that's 4 rotations. Well, I counted 5. I physically went 5. Okay, so if I want to go 4 back, there I am. If I want to go straight down, that's 2 more. There it is. If I want to go all the way up, it should be 4. There it is. So I think it's a lot better now. And it can probably still be optimized either in the sketch for the board or in the dial settings for rotating in here. So now I'll try the other physical joystick on player 2, the Happ Controls one, because it is a little different. Okay, I'm only controlling the blue guy. So if I try to go 1 at a time, so that seems to be cleanly going around with individuals. I'll go the other way. And now, if I start trying to go 2 over and 2 back, okay, it seems to be debouncing these contacts. I just want to see for now it does generally work. So if I try to go 3 controlled, not necessarily extremely fast movements, I should point diagonally down, then back up. So for now, I think this is a lot better than it used to be.